Okay, class. So starting with Doppler's effect, this is the last topic that is left. So apparent change in frequency of sound due to relative motion between source and the observer is called Doppler's effect. Basically, there's a source from which sound is coming. All right. And there's a observer. Observer we call where the sound is reached. This is the source, this is the observer. And we take a sign convention that is from the source to the observer. If we move like this, if the sound is moving like this, we take it to be positive. If opposite occurs, that is from observer to source, we take this as negative. All right. So how do we calculate the apparent frequency? Apparent frequency is calculated by velocity. Velocity, this is the velocity of air minus velocity of observer by velocity of air minus velocity of source and the original frequency of the source. This will give the apparent frequency. This is the apparent frequency, and the medium is at rest. The first thing is that medium is at rest. But remember, sign convention is very important. That will determine whether this will be minus, this will be plus, or what. So, okay, if source and observer move towards each other, the apparent frequency increases. If source and observer move far away from each other, then the apparent frequency decreases. So, nu naught is the actual frequency by the source. V is the velocity of sound. V naught is the velocity of the observer. Apparent frequency that I already told you, and Vs is the velocity of source. All right. So this is the apparent frequency which we have calculated. That is V minus V naught. Now see, if suppose V naught is negative because of the sign convention, this is negative. So minus, you will put here minus. If suppose Vs is negative, then you will put V minus Vs like this, and then your original frequency. So this is the sign convention. From source to observer, it's positive. Observer to source, it's negative. This means, see, what is the meaning of this? Is that this is the source, this is the observer. Suppose the direction of velocity of source is this, and observer is also moving towards it. Now, what is our sign convention? Remember, one sign convention, other will be opposite. From source to observer, positive. So this will be positive. So automatically, your Vs becomes positive, Vo becomes negative. This is how you have to take. Suppose that's different examples can be there. One can be at rest. Many questions are there where your observer is at rest. One more example. Suppose this is the source, this is the observer. Source is moving in this direction. Observer is also moving far away. That will decrease it. Source to observer, positive. So here Vs will be negative and Vo will be positive. We'll see a question also. First, write it down. Doppler's effect.
Ma'am, V is the velocity of the source.
V is the velocity of air. 320, we take 330. 330 usually take 330 meter per second. Source is this.
Okay.
Okay, look at this question. This is that this is a vehicle, this is the source, this is the observer. So this is moving with 10 meter per second, this is moving with 5 meter per second. Both the directions are mentioned. This is the original frequency, 1000 hertz. And speed of sound is, here it's given 300 meter per second. If not mentioned, the speed of sound in air, we'll take it as 330 meter per second. There's the speed of sound in air, which I was telling you, speed of sound in air, V, this one. This is mentioned here as 300, so we're taking it as 300. Otherwise, this is generally taken as 320 or 330 meter per second. So see, from the source, see, this is the source, this is the observer. Source to observer, this direction will be positive. So for us, speed of the source will be plus 10 meter per second, while the speed of observer will be negative, minus 5 meter per second, because it was moving towards it, no? And velocity v is given as 300 meter per second. And what else do we have? Frequency. Frequency is 1000 hertz. So formula is v minus v naught by v minus vs into the original frequency. This is the formula. If we substitute in the values, we'll give 300 minus, this is minus 5, this is 300 minus 10 into 1000. So frequency will be 305 by 3, no, 290. One thing, do not round it off here. Otherwise, if you will round it off here, your answer will directly be exactly the original frequency. There won't be any difference. So this is 305 to 90. You know, almost this is 1. 305 to 90, very slight difference. Right? But take the exact values. So frequency will be 1051. Write it down.
Ma'am, the unit will be hertz, right?
Yeah, the units will be hertz. Okay, before we start with the trigonometric function, now here in this lesson, in oscillations, trigonometry will be used a lot. So there are some identities which you already know. All of these identities, cos theta minus pi minus theta, sine pi minus theta, pi by 2 minus theta and all. But still, since this will be used here, and this one more conversion, 1 degree is equal to pi by 180 radian. So just write at a place all these identities. These use this side, you don't need to write, this side you already know, this entire column. Then
And
we,
this is part of waves.
it's a part of oscillations.
Okay.
Waves is over, oscillations I'm talking about. See, SHM, simple when we are talking about the harmonic motion. So there are two things that occur apart from simple harmonic motion. One is periodic motion, one is oscillatory motion. So the motion that is just repeating itself after a regular period of time, that we call as periodic. From the term periodic only you can derive the term that this is related to time period. So like examples are revolution of earth, that is periodic motion. It's periodic motion and it has a time period which is fixed, 365 days. Similarly, revolution of moon around the earth is periodic. It has a definite time period, that is 1 day, which is 24 hours. Right, so these are all periodic motion that are depending upon one time period which is getting repeated and repeated and repeated. When we're talking about oscillatory motion, see, periodic motion can occur in any pattern. It can occur in any direction. When we're talking about oscillatory motion means there is one mean position and there are extreme positions. So if a body is moving to and coming back to and fro, this periodic motion, repetitive motion, is called oscillatory motion, or we say it's vibratory motion. Example, if you take a thread and you tie a small bob towards the end and then you rotate it. So the swinging of pendulum motion is an oscillator, it is moving. Or spring mass system, when you compress the spring and release it, the spring covers to and fro motion for some time, and then when the entire momentum is lost, when the velocity becomes zero, it finally comes back at rest. So this is the difference between periodic motion and oscillatory motion. When we are talking about simple harmonic motion, for simple harmonic motion, there are certain conditions to be followed. So a particle is said to execute simple harmonic motion if it moves to and fro about the mean, that is the equilibrium position, in a straight line, and the graph between displacement of the particle from equilibrium and time is a sinusoidal or cosine curve. This means, this I'll tell you, we'll see the conditions. Like type of oscillatory motions is, suppose this is a bob. This is going to its extreme position, coming back. Again going to its extreme position, coming back like this. This original position is known as the mean position. This is the spring, this is the mass. This is the mean position. Mean position. Mean position means original mean position. So suppose I have compressed it. So it will move, it will be compressed, it will move. It will be compressed, it will move. Or one more example is, if a U-shaped tube is taken, same tube which we've studied in fluids. This is filled with fluid. On one side, if you exert pressure, so this will move up, move down entirely. When this will move up, this will move down. This will move down, this will move up. So there is an oscillatory motion between this also. Now, what are the conditions for SHM? Firstly, it has to be oscillatory motion. This has to be an oscillatory motion. Secondly, restoring force should act towards the mean position. Lastly, the force which is acting is directly proportional to the displacement from the mean position. And we write it as F is equal to minus Kx. K is a constant for different systems. This value of constant will be different. X is displacement from mean position, and this negative sign shows that restoring force acts towards mean position. Towards mean position. So why negative, why not positive? The reason is that always mean position's direction will be opposite to the external force. Correct? That's why. Write down all these points of SHM.
Ma'am, I had asked a question in WhatsApp. Can you help with that question?
You've sent a question.
Yeah, ma'am. I sent it before.
Let me just check.
Okay. And it's from thermodynamics.
Okay, in changing the state of gas adiabatically from an equilibrium state A to another equilibrium state B, amount of work is equal to 22.3 joules on the system. If gas is taken from A to B via a process in which the net heat absorbed by the system is 9.35 calories, how much is the net work done by the system in the later case? 1 calories. Okay. See, firstly, the work done on the system is 22.3 and the heat absorbed by the system is 9.35 and the conversion is also given. So change in heat will be what in this? Since it is adiabatic, change in heat will be 0. So the change in work done that is being done will be minus 22.3 joules because work has been transferred, right? Work has been
Yes.
done. Work is done on the system, no? So we put a negative sign as a sign convention. So you must, from the first law of thermodynamics, you must be aware that delta Q is equal to delta U plus delta W, that equation,
Yes.
right? So you can find out delta U. When adiabatic is in adiabatic process, directly it is negative of work done. So it will be, if work done is minus, so delta U, that is the internal energy, it will be plus 22.3 joules. Right. Now
Yes.
see, when we are talking about the heat, firstly, you have to convert the heat. In this question, it's written 9.35 calories. So if we multiply 9.35 into 4.2, 9.35, let me just calculate. Around 40 it would come. Let me just check. 9.35 into 4.1, 39.176. So this is the heat. Now see, delta Q, the new value which you have to find out, right? Net work done is our question. So the new heat, right? Work done that has been absorbed. When you substitute in the values to find out the heat, let's say this heat was the other heat. No, one heat was 0, which we had taken initially because of the adiabatic system. This second heat is absorbed by the system, right? So from here, you have to find, the value of delta U now. You know the value of delta Q. You can calculate work done. So,
So delta U of both the states will be equal.
yes,
Delta U of both the equilibrium states will be equal.
delta U will be the same. Delta U will be the same. It's the internal energy of the system. Delta U, which we have calculated from the first part of the adiabatic system, right? That
Yes.
will be equal to the process, the second process it's given on this third line which you've written, taken from A to B via
Yes.
process in
Yes.
which net heat absorbed is this. Delta U will be the same because it's the internal energy. You must have heard of the extensive and intensive properties.
Yes.
So because of that, this will
Oh,
occur. Delta
oh,
U will be same. So one work done was 22.3 है ना, this one, yes,
Yes.
that was 22 minus 22.3. And the other work done would be exactly the heat only. Work done will be, how much work done will be, 39 point something was obtained, 39.176 I said, I think 39 point something was there. That was the heat minus delta U, that is 22.3. Whatever will be left, that will be the work
Oh,
done. See, delta Q is 39.176 joules. Delta U is the same 22.3. So work done will be what? You'll subtract only both of these. So I think 9, then decimal 6, 1, then 9 minus 8, 1. 16.9 joules around. This would be
okay.
16.9 something. If you subtract 39.176 from 2.3, uh, this should only come 16 point something or 17, like this. Orally, I'm just doing it. If you want, I can give you in writing also with proper calculations, but around this only 16.9 or 17, your answer will come.
Okay, ma'am.
Clear
Okay.
now?
Yes.
Okay, now the last topic for today, that is the conditions of characteristics of SHM. So first is the displacement. So displacement is basically it's taken from the mean position, and F is equal to minus kx. This already I have discussed. But an extension of it, when we talk about the second component, that is acceleration. Acceleration will be force upon mass. If I put the value of force as minus kx, this will be by m. One more thing, acceleration is dv over dt. But if I want to write it in terms of displacement, I'll write it as d square x over dt square. That is the double differentiation, right? So both are of these are what? These are accelerations. I can equate it. Minus kx by m is equal to d square x by dt square. Correct. So if I bring this on this side, this over this side, d square x by dt square, this will be plus equal to 0. One thing, Harsha, k by m. I don't know if I've discussed this earlier or not. Omega square is written as k by m. So omega is written as under root of k by m. Omega is what? Omega is basically the angular
Ma'am,
frequency.
what is K?
K is a spring factor, we say. It's a constant. It's just that for different systems, we have different values. It's a spring factor, we say. Suppose I have given you spring mass system. So this K will be called as spring constant. And if
Oh,
I give you pendulum, suppose pendulum system. So value of K is 2 pi. We have an equation for time period. T is equal to 2 pi under root L by G. You must have heard of it. We have done it in the starting also, dimension analysis, if you remember. So there the constant. So it's like a constant. It's a constant only, but it's just that for different systems, it's different. That's why I am not writing it as specific. I'm writing it general. No, I'm not writing it specific because for different systems, it will vary.
okay.
This is angular frequency, or you can say even velocity. Angular velocity is also fine. So final equation will be d square x over dt square plus this is omega square x is equal to 0. This is known as second order differential equation of SHM. Second order differential equation of SHM. Second order differential equation of SHM. This is known as it. So we write this equation, so the solution of equation of SHM, both of it which we have already studied in waves. X is equal to a sine omega t plus phi naught, and x is equal to a cos omega t plus phi naught, where phi naught is the constant. Note it down quickly. You can leave if completed. On Thursday, we'll continue this. Thank you so much.
Thank you, ma'am.